All right, class, you've just finished taking your little quiz, your 2.1, 2.3 quiz. Now it is time for some algebra review and a couple of new postulates. The fun fact, I just recorded this whole video. It took me 28 minutes, and then it didn't actually record my screen. So this is a take 2. I might move a little bit faster. I don't want this to be a 28-minute video. So here we go. If you want to pause it really quickly and go through these properties of real numbers, go for it. See what you remember from algebra. Once you're done writing down all of your ideas, unpause it and I will go through them with y'all. All right? So, first, the commutative property. You can remember the commutative property by the letters that are in the word commutative. So, CO, commutative property, we are changing the order. So, CO, commutative, change, order, changing order. So an example of this, let's say we had the equation 5x plus 3 minus x, or we'll say plus x, equals 20. Our commutative property says I can change the order of this left side, and it's still going to equal the same thing. So let's say maybe I wanted all my x's closer together so that I could combine like terms a little bit easier. We are allowed to change that order. So we can write it as 5x plus x plus 3 equals 20. So I changed the order of that left side, but our commutative property of addition says that that is still the same equation. Next property is our associative property. Our associative property is our regrouping property. So we're going to be regrouping. And this you'll see whenever we've got parentheses in our problems. So if we had the problem 3 plus 5x in parentheses plus x equals 20. Our associative property, we're going to regroup. So I'm going to change these two parentheses and put them around a new group of numbers. So instead, I could write 3 plus parentheses 5x plus x close parentheses equaled 20. So notice what I was grouping changed. First it was the 3 plus 5x. Now it's the 5x plus x. I regrouped, and that is going to be the same equation as the first time. Next is the transitive property, which last class or 2 classes ago we talked about law of syllogism, which related to the transitive property. So kind of full circle here. Our transitive property is going to say if A equals B and B equals C, then A equals C. So like the law of syllogism, we can take that common part, B, and we can cancel them out. So if we took out B here, we took out B here, we'd just be left with A equals C. So like the law of syllogism, we've got the transitive property. Next, the reflexive property. So this is a really easy one. Reflexive property just says some number equals itself. So x equals x, b equals b, 3x equals 3x. So both sides of your equation are the same. Both sides of the equation are the same. Then we've got substitution. So if you think of the word substitute, you're just going to be replacing something with a given value. Or if you think about a substitute teacher, if I'm not here, a substitute is going to come into the classroom and going to replace my position. They will be the teacher for the day. So substitution, we could say if A equals B and B equals Y. No, let's erase that. Let's erase that, because that was more like, that was similar to the transitive property. We'll do a little bit better. If Ax equals B, here we go, and X equals Y, then AY equals B. So that's better. Anytime I see X, I can plug in the value of Y. So instead of ax equals b, I took my y and I plugged it in for x to give us ay equals b. So that's substitution. Next is the addition property of equality. We can abbreviate this as APO, addition property of equality. So basically, the addition property of equality says if you add something to one side of your equation, you have to add it to the other. So if A equals B, then A plus X equals B plus X. So I added the plus X to the left and plus X to the right. So that addition on both sides keeps my equation equal. Okay, so similar to APO, there's also SPO, MPO, and DPO. So hopefully we can use our reasoning skills. That's going to be the subtraction property of equality, the multiplication property of equality, and the division property of equality. So if you subtract on both sides, your equation stays the same. If you multiply on both sides, your equation stays the same. Or if you divide by both sides, the equation will stay the same. All right. If you wanted some examples, you could have A minus B, A minus X, equals B minus X. So we're subtracting X on both sides. Here we have A times X equals B times X, or A divided by X equals B divided by X. So starting off with that regular equation, if A equals B, those three things happen. So that's just a side note. Definitely want to take note of that. Two more, and then we'll look at an actual proof. We've got the symmetric property. So the symmetric property is when you switch the sides of your equation. So switch sides. This is different than commutative property, okay, and we'll see why. So our symmetric property basically is just going to say if x equals y, then y equals x. Okay, so I just switched the two sides of my equation. Okay, that is different than the commutative property. The commutative property, you're switching one side of the equation. This one side changed order, but your symmetric property, the two sides are physically switching places. And then our last one is the distributive property, which hopefully we know this from algebra. It should be embedded in our brains. So basically you're going to have some coefficient, I'm going to call it an uppercase A, with parentheses, and inside the parentheses will be multiple terms. So I'm just saying x plus y plus z. Those are my three terms. With the distributive property, you're going to take that coefficient and multiply it with each term. So a times x plus y plus z ends up equaling ax plus ay plus az. And that is the distributive property. Okay, so hopefully that was a review. I kind of went through that quickly. If you need to re-listen to some of those, go ahead, rewind the video. If not, we will go on to our proof. So the directions do say with a partner to complete the proof, but since we're reviewing this just kind of on our own, your partners, your people around you may not be done with that test, and I just want it to stay silent until everybody is done. So let's just go ahead and do this proof on your own. Okay? You can pause it and try and do it on your own, or just follow along with me. I'm going to label my different steps, my different statements. 1, 2, 3, 4, 5, 6. So these statements are just the steps we're using to solve. Steps to solve the equation. Our reasons are going to be the justifications or the properties that we just reviewed. Properties. Okay, so you're going to have a given statement. Our given statement is y equals 2 times 3x plus 4, and we know that y equals 20. We're trying to prove that x equals 2. So basically we're solving this given equation to get our proof statement. Alright, so in this proof, you just start out with your first statement, and you must see where did that come from. all the time, this first statement is just given. The reason it's given is because, hello, it's given to us, so given. All right, I'm getting a little sloppy up here. Next, we want to look and see how do we go from statement 1 to statement 2. Okay, so to get from 1 to 2, notice I see the y turn to a 20, but everything else is the same. So why did y turn to 20? Oh yeah, I remember y equals 20, so I used that substitution property, substitution, to plug in the 20 into my equation. Okay, now how did I get from step 2 to step 3? What's different? The 20 is the same, but something over here on the right side has changed. Okay, 2 times 3 gives me that 6, and 2 times 4 gives me 8. Okay, I remember that's going to be the distributive property. I took my coefficient 2 and I multiplied it by both terms to get 6x plus 8. Now from step 3 to step 4, what happened between 3 and 4? So now I've got 20, it's a 12. Instead of 6x plus 8, the 8 has disappeared. So we know, how do we get rid of a plus 8? Oh, okay, we subtract 8 on the right. If we subtract 8 on the right, we also need to subtract 8 on the left. And in fact, 20 minus 8 gives us 12. So when we subtract on both sides, remember that is going to be SPO. So that is subtraction property of equality. We subtract on both sides. 2 more. To go from 4 to 5, I went from 12 to 2 and 6x to just x. Well, I know to get just an x, I have to divide that right side by 6. If I divide the right by 6, I also need to divide the left by 6. So when you divide on both sides, that is depot, division, property of equality. And last but not least, this step is kind of unnecessary, but it's written in the proof, so we do need to justify it or reason it. I noticed that we had 2 equals x, which changed to x equals 2. So my sides switched. When your sides switch, that is the symmetric property. And there is our proof from start to finish. All these little lines I drew in here, you don't have to. I just like to think about each step-by-step part. Okay, so that should have been a review. If you need to rewatch something like that, go for it. You can find other proofs online. But we're going to move on and look at proofs for geometry. In geometry, we're going to have some different postulates. And we're going to start out with postulates 5 through 11. These postulates are on points, lines, and planes. Obviously, it says points, lines, and planes postulates. So you don't necessarily need to remember that postulate 5 says this statement. You just need to remember all of these statements. So these postulates 5 through 11, this right side, you need to know these sentences off the top of your head. They are common sense and common knowledge, but you do need to be able to think of those when you see points, lines, and planes. All right, so we'll go through, fill these in, and then look at a couple of illustrations down there. So postulate 5 says, through any 2 points, there exists exactly, we'll say, 1 line. So if you have 2 points, 1 line goes through those 2 points. Postulate 6, a line contains at least 2 points. Okay, so if we were to put those into if-then statements, those would be the converse of each other. Those are the opposites of each other. Postulate 7, if 2 lines intersect, then their intersection is exactly 1 point. We learned about that during our first unit. 2 lines intersect at 1 point. Number 8, through any 3 non-collinear points, there exists exactly 1 plane. So if we have 3 points that are non-collinear, so not in a straight line, there will be 1 plane that contains those 3 points. And then postulate 9, a plane contains at least 3 non-collinear points. So similar to 5 and 6, we can see that postulates 8 and 9, if you write them as if-then conditional statements, they would be the converse of each other. They're opposite. Postulate number 10, if 2 points lie in a plane, then the line containing them lies in the plane. And lastly, 11, if 2 planes intersect, then their intersection is a line. So 7, 11 come from last unit's notes. We learned about that. Then everything else comes from last unit notes too. We specifically said 7 and 11, and all these other things are just some common sense statements that we should be able to remember. Here's just a little debriefing about the midpoint theorem. So we have, if M is the midpoint of AB, then AM is congruent to MB. So that is a true statement. If we're told that M is in the middle of AB, midpoint means middle, right? Then we know that it's cutting this segment into 2 equal pieces. So from A to M and from M to B, those are going to be congruent. So our question is the midpoint theorem a biconditional? So we need to know what the word biconditional means. That means, can we read that statement forwards and backwards? Is the conditional true and is the converse true? So we are given this conditional. We need to write the converse. So I'm going to rewrite this as the converse. We're going to switch the hypothesis and conclusion. So if AM is congruent to MB, then M is the midpoint of AB. So I know this first statement is true. So we need to see, is the converse true? So if AM, right here, is equal to MB, then M is the midpoint. Yes, that is true. So my original conditional and my converse are both true. So yes, we can write the biconditional of the midpoint theorem. You can read that forwards or backwards. So that's just a fun fact, something cool to think about. And lastly, so I hope I'm not going too fast, trying not to take up 28 minutes of your time right now. But these last 3 are just looking at diagrams and then thinking about our different postulates. So if you want to take a pause, look over the postulates and then answer these 3 questions, you can do that. You can just keep chugging along with me as I just go through them. Let's use a pretty color. Let's use hot pink. I like pink. So number 1, we want to state the postulate illustrated by the diagram. So you need to be able to identify the different pieces of our diagram. And then we can scroll back up or flip your page or wherever it is, look at your notes, and think about the different postulates that we have. So I know this is 2 lines intersecting. And then I know we're highlighting this point. So we could read this as, if 2 lines intersect, then they form a point. So we want to look at our different postulates, which one says that. 2 lines intersect, then their intersection is exactly 1 point. Wow, that is going to be postulate number 7. Woo, postulate number 7. Easy peasy. Then number 2, same type of deal. This time we have 2 planes intersecting. Not 2 airplanes, but 2 planes. And then I noticed that we have a line. Oops. A line is highlighted here, so this is a line. So if 2 planes intersect, then they form a line. Great, that's going to be postulate number 11. It's easy as that. As long as you can identify the different diagrams, you can basically write the postulates without even having them memorized. Okay, and then this last one, number 3, we want to use a picture to give examples of postulates 9 and 10. Okay, so postulate 9 says a plane contains at least 3 non-collinear points. So we need to find one plane that has 3 non-collinear points on it. So notice there's plane Q and plane P, and they're points A, B, and C. So I need to see which plane are points A, B, and C on. Looking at this, I see that plane P contains A, B, and C. And that is my postulate 9, because A, B, and C are non-collinear. Postulate 10 is a little bit more complicated. That's the postulate that says if a plane contains 2 points, then the line that contains those points is also on the plane. So I need to find a line on a plane with 2 points. So I see that line N contains A and B. So line A contains points A and B. I also know that plane P contains points A and B. So since plane P contains those 2 points and line N contains those 2 points, I know, oh shoot, did it disappear? Oh no. Ah, sorry, I'm going to make y'all seasick. I think I hit that button. Oh my goodness. I know, sorry, regroup, line N contains A and B, plane P contains A and B, so therefore plane P contains line N. Perfect. Those are some examples. Okay, so hopefully that made some sense. You can go ahead and grab the homework from the front desk. Hopefully I remember to put it up there. Grab the homework from the front desk. You can work on that for the rest of class. And then if you have any questions, please clarify with me. I'm probably in the room right now looking at you, being awkward. So I know y'all are listening to my voice. Anyways, that is today's lesson. Hopefully you did well on your test, quiz, and understand these notes. Let me know if you have any issues with anything. Bye, students.